So we have one of our parent graphs, the square root of x, and they happen to take a specific point, in this case 16 comma 4. And what they're going to look at is the following different colored graphs. In the blue graph, we have 3 times the square root of x. And in 3 times the square root of x, the corresponding point is 16 comma 12. On the green graph with the 2 in front, we have 16 comma 8. On the orange graph, we have 16 comma 2, and on the purple graph, we have 16 comma 1. And what we're going to look at is these specific points. If I take my red graph, 16 comma 4, and it goes to my blue graph, 16 comma 12, what has happened? What has changed? The y value has changed. How do you get from 4 to 12? Your y value has been multiplied by 3, which is what you see in front of the equation. And so when something is outside of the function, and that 3 is outside of the function, you can make a little bit of a note beside this graph that this affects the, there we go, wow, that's pretty. This affects the y values. Look at the green graph. If I started with 16 comma 4 on my original graph, and on the green graph, I went to 16 comma 8, my y values were multiplied by 2. From my red to my orange graph, again, I started with 16 comma 4. I went to 16 comma 2, my y values were multiplied by a half. And finally, on my purple graph, I started with 16 comma 4. I went to 16 comma 1. My y values were multiplied by 1/4. And this pattern of what's happening to your y values happens everywhere, to every single point. For example, if I pick another nice point on my square root graph, here's another point, square root of 4 is 2. Let's just check it out on our blue graph. What happens on our blue graph at the same thing? We got 4 comma 6. Do you notice that your y value has been multiplied by 3? And this happens no matter which point you start with. If you started with, there's another nice one. Here we go. 9 comma 3. I go up to my blue graph. Straight up from 9, I get 9 comma 9. Is my y value been multiplied by 3? Yes, it has again. So whenever we have a number in front of our function, it's going to affect our y values. And it's going to do exactly what our gut wants it to. You have 3 times the square root of x, we multiply our y values by 3. Next up, we look at what happens when there's a value inside. And here too, they've got a starting point for us on the red graph at 4 comma 2. On the blue graph, they've got the point 1 comma 2. On the green graph, 2 comma 2. On the orange graph, 8 comma 2. And on the purple graph, 16 comma 2. So this time when we go from red to blue, we notice that it's our x coordinates that have changed. So beside the first one we said it affected the y coordinate. In this one we can say it affects the x values. And it goes against what we want it to. Having that 4 inside the blue graph, you might want to say, oh, I'd like to multiply my x values by 4. But we're going to find out that almost everything that happens inside the function is opposite of what you would like, right? Because the plus 2, you wanted to move it 2 to the right. What did it do? It moved it 2 to the left. The 4 that we have inside the square root, you would want that to multiply your x values by 4. Instead, we always multiply by the reciprocal. Multiplying by 1 over 4 is the same as dividing by 4, but multiplying by the reciprocal is going to be easier, especially once you get to fractions, because dividing by a half isn't the easiest thing to do. So we're always going to talk about multiplying. So when we look at the different colors, on the green one, I went from 4, 2, sorry, not 4, 4, 2 to 2, 2. Here I've multiplied my x values by 1 over 2. On the orange graph, I went from 4, 2 to 8, 2. The reciprocal of a half is 2 over 1. I've multiplied by 2. And finally, on the purple one, the reciprocal of a quarter is 4 over 1. And you've multiplied the x values by 4. So having that value inside the function either stretches it or compresses it horizontally. And it does so by multiplying by the opposite of what you would think, multiplying by the reciprocal. And finally, if we were to combine them all, we look at the points that we have, and this time they're starting again with 4, 2. They've labeled the point 2, 8 on the blue graph, the point 2, 4 on the green graph, the point 8, 4 on the orange graph, and 8, 1 on the purple graph. And if we look at the point 4, 2 going to 2, 8 on the blue graph, and the equation of the blue graph is y equals 4 times the square root of 2x. So first of all, do we notice that the 4 is outside of the function and the 2 is inside of the function? So things that are outside of the function are going to affect the y values. And they're going to affect the y values exactly as you see them. Does it make sense that we would write above here that you would multiply your y value by 4? Is that what happened from my coordinate? I had 4, 2. It's now the y value is 8. It's been multiplied by 4. And the 2 inside, that would tell you to take your x values and multiply them by a half. And so the point 4, 2 gets transformed In this case, stretched vertically, then squished horizontally, and ends up at 2, 8. So what's going to often happen in these questions is you'll be able to say, I know on my red graph, because I've memorized what my square root graph is, I know I have the point 4, 2. I want to find out where that point goes on my green graph. And I don't know it's at 2, 4 yet. I know we've labeled it. We're cheating. We can see that it's going to be 2, 4. But we'll look at the equation and say, ooh, I have a 2 out front. That tells me I should multiply my y values by 2. And I have a 2 inside. That tells me I should multiply my x values by 1 over 2. Well, if I multiply my x values by 1 over 2, 4 times a half is 2. And if I multiply my y values by 2, 2 times 2 is 4. Is that the point we labeled, 2, 4? Yes, it is. So the process is you'll take the points that you know from your original graph, 4, 2. When I go to my orange graph, I'll look at my equation and I'll say, I know that this 2 multiplies my y values by 2. I know that this half would multiply my x values by the reciprocal, 2 over 1, which is just 2. Where does that go? X by 2 will make that 8. Y by 2 will make that 4. And finally, with the purple one, sometimes the nice thing about doing something over and over and over again is hopefully by the last one that we get to, you're like, yeah, I get it. At 4, 2 on the purple one, I've got a 1/2 in front. That means I need to multiply my y values by a half. I've got a half inside. That means I multiply by the reciprocal, 2 over 1. My x by 2, that'll go to 8. My y by a half, that'll go to 1. And sure enough, it matches up. So on the next page, they have some more notes of the same things. A couple of things that they show. First of all, if you had 2y equals x cubed, you could rewrite that to get the y by itself. I would rewrite it by dividing both sides by 2. Can you see that this would multiply your y values by a half? And sure enough, the point that they looked at 8 goes to a point at 4. And on the orange one here, they've got a 2 in front. That would multiply your y values by 2. Okay? Some of the language that we'll use. When you multiply y by a half, we will call it, wow, can't spell today, vertical. And anytime you're squishing something, we use the word compression. And then you write by a factor of 1/2. Whenever you are making something bigger, we call that a vertical stretch. And that's by a factor of 2. So we either stretch or we compress, depending on what we multiply by. If we look at, this is the same one, but now it has some negatives involved. We can actually combine what we do with our reflections and our stretches at the same time. Because remember, a negative outside the function multiplied it by a -1? multiplied your y values by a -1, and now we're also going to multiply our y values by 2. If you're multiplying something by -1 and you're multiplying it by 2, it just makes sense to do them both at the same time. So what happens when you have y by -2? Okay, when your y values are becoming negative, we have a vertical reflection over the x-axis and a vertical stretch by a factor of 2. So at the box at the bottom, it highlights that whenever your value of A is between 0 and 1, we're going to call that a vertical compression. And whenever your A value is bigger than 1, we're going to call it a vertical stretch. The negative in front is just a reflection that goes with it. So we're going to look at our first example. Here's the graph of y equals f of x. We want to sketch the graph of y equals -1/4 f of x. So some of the things that you're going to do, and because it uses lots of words, we're going to label that this is a vertical reflection. Are you okay with VR? Vertical reflection. And the 1/4 is a vertical compression. That's to describe what's happening. We can combine both of those together and say we're going to multiply our y values by -1/4. Now on our original graph, we need to look at what are some of the key points that we have. This is an absolute value graph. This point at 0, 0 is very important. And what I need to do is I need to multiply my y values by -1/4. When showing our work, we're going to do this. We're going to take some points, and above the arrow, and the arrow is going to represent, this is where this point is changing to. I'm changing 0, 0 to something new. And above it, I'm going to explain what mathematics I'm doing to change this point. My y values are multiplied by -1/4. Well, in this case, what is 0 times -1/4? 0. This point becomes 0, 0. So technically, on the blue graph, that point didn't change. Now, I could pick any other point on my red graph. But if I wanted to deal with whole numbers or integers, what would be a nice value to use off my red graph if I know that I have to multiply the y coordinates by -1/4? Like I could choose 1, 1, but then I'm going to get a fraction, which isn't bad, just not as nice to graph. Can someone tell me a point I could take off my red graph so that when I multiply the y coordinates by -1/4, I don't get any fractions? 4, 4, yes. If I took 4, 4, which is right here, and I multiplied my y value by -1/4, I would get, my x doesn't change, but 4, -1. So I go to 4, and I go to -1, which would be right there. I could choose another point that works out nice. Hey, maybe I choose -8, 8. If I multiplied My y value is by negative 1/4. I would get negative 8, negative 2. Negative 8, negative 2. Connect the dots. And here's my new graph. Stating the domain and range of each function. On my red graph, my domain was everything. My range was bigger than or equal to 0. On my blue graph, my domain is still everything, but my range is now less than or equal to 0. Couple of other things. Everything in this question was in function notation. So the original graph was given to us as just f of x. And the transformation was given to us as y equals negative 1/4 f of x. This is one, since you recognize it, that you could write the actual or explicit equation for. The original one, can you see that its original equation is the absolute value of x? That's one of the ones that we learned. What would be the actual equation of the blue one? The actual equation would be, well, there'd be a negative 1/4 in front of the function, so it would equal negative 1/4 absolute value of x. Question number 3 for practice.